So with this, I would like to welcome our last speaker of the day, and that's Harsha Master. He's a system architect at NXP Semiconductors, working with programmable basebands and active in the 6G for All initiative. And I'll let you go. Yeah, it's the last of the day.
Not the least.
Yeah.
Thank you. Thank you. And I think after so many presentations from the morning, I think everybody has given sweet drinks, cocktails, mocktails. But now I think it would not be like a water. I'm just, okay. It's, all right. So let me introduce myself once again. So I am Harsha Master. I work in CTO office of NXP as an principal system architect. I look after most multiple domains in the system because it's not just the 6G, but 6G is one of the areas. And also, before I start my presentation, I also say NXP is a semiconductor. We talk about silicons. We do not talk about too much of the software. And what I'm going to talk is mostly about from my department. So NXP is a big, and there are many organizations inside NXP, and this I would like to restrict to the system innovation department, what I have. Anyway, my previous speaker gave a very good pitching, and also the previous presenters gave a lot of insights about the AI. It's fair. Like, we all talk about AI. Nobody is now escaping the domain of AI. And in our perspective, yes, we are also working on AI, but our domain is more towards the devices. I think that's the differentiator. All the speakers probably talking about network side, infrastructure side, and I'm here to talk about the device side, and also not the like traditional modem, traditional 5G device. I'm talking about the smart devices, which needs the communication, which needs the smartness likewise. And as you see that NXP has a lot of portfolios in his basket. For example, just to give an classifications, we have many type of CPUs, MPUs, MCUs. This is basically, you can see like classifications from the CPU, GPU, DSP. The combination of these cores and technology towards the processors, we have a different processors like compute processors, network processor, baseband processors, numerical processor is NPU, AI. At the same time, the combination of CPU and NPU can also give different application processors. It's very specific. For example, if you want to use a CPU towards an automotive device, it's different. If you want to use a processor towards a drone, it's different. If you want to use a processor towards the network underlying infrastructures, it's different. For example, your security cards, for example, the credit cards, the processors are different. So combination of such devices are towards application thing. I don't have any too many readings. I just have pictures. So please be cooperate with me here. So just to illustrate the portfolios, how do we in the system innovation we pick up different processors. The most important thing is to understand what is the target. What is the target to build? And here I have taken what it takes to build a smart device with capability to build a communication device, probably a RedCap UE. In such case, what we need? We need a compute processor which can run your software. We need a baseband, for example, to convert your analog to device, digital to analog, and also give infrastructure towards the baseband. I will also, for example, if you need a modem, you also need some kind of security. For example, you need a SIM card. We also have a profile which is UICC, where the eSIM is written. As such a device, it also embedded. You can combine this as one system. It's not an integrated system, it's a discrete system. So combination, how do we merge these silicon will produce you into a system like this. It's just an illustration as an example. And you can also see this picture also resembles software-defined radio. So, for example, on the right side, we have in the green box, we have a compute processor, which is an industrial-grade processor. And this processor has multiple ARM core. It also has an NPU, which can do up to some TOPS. It also have a security systems, which is security cores, which we can integrate with the LA9310, which is typically a baseband. So it has also ADC DAC, means it can do the analog to digital conversion directly at that point. And also it has a DSP-like core where you can do your accelerations. So SN220 is an example where you can integrate directly to the platform to integrate your security. For example, you want to have a crypto accelerators. Or you can also use eSIM. And the third one is to integration towards the RF, means the output of LA9310 is IQ, right? So you need somebody to get into the air, the front-end module. That is hardware changeable, means you can pick up anything. Currently, we use Lime STR, Lime Micro RF. It's also possible to use different RFICs. So what I'm trying to explain here is, if you look at this, the combination of this application processor, which application processor you take, we can target any application-specific end device. It is not that traditionally I have a generic platform, I put in modem, then I write my own. So no, in the existing infrastructures like robotics, automotive, it's very specific. You need to be very, very realistic. So such a thing, for example, the 5G clock which runs here is a thermal caged oscillator. Means you put this device in the oven, it will behave like generic. Means it can go up, it can take up to the higher temperature. So such a design only comes with such a kind of a discrete possibility. So if a generic modem may not be sufficient, but I'm not saying that everywhere it is possible. Such an oscillator needs conditionally designed in such a way that it protects in a several atmosphere. For example, this device is used in industrial floor. You need a certain degree of what you call tolerances. So this is just an example what I was trying. It's also, we built from the system innovation, we tried to give up one of these ideas to our partner. This is not just in the papers. This product is available from one of our vendor, RFNM. I think most of you probably have also heard and have this kind of device. This device consists of IMX, which is a CPU, And also, you can replace different RFs. For example, if you want to use Lime, you can, on the second slot, you can replace, currently this one is Metanoia, you can replace. And also, depending on your use case, which you can build your own. This kind of platform is not just pictorially the big. The same architecture, we just reduce it by 4 by 4 centimeter. Everything is same, except that we have to fix the RF. All the features what was there in 20 by 10 centimeter infrastructure, the prototype, is squeezed into 4 by 4 centimeter, except that the RF is built in and it can do N78, N77, mid-band, low-band, high-band. This is also should be available from the RF. These are the past thing. What is more exciting is we have recently working with LimeSTR. And this is also one of the NXP's baseband. And this is ready to plug in. I don't want to talk about too much because tomorrow my friend is here who will also give more detail on this product. And also there is a demo also be there. So I will come back to the AI again. So for example, why our system innovation makes a different perspective here is taking the line as the RF SDR. We can also use NXP's own NPU. It is a discrete NPU. We can combine these two, put it into a development board, and you can make use of all the things. See, imagine your OAI is running this. It is not imagine, it's already running on this, except that it is in the testing phase. You can use the NXP's baseband, which is develop, the LimeSTR developed the board here. And also the LimeSTR has providing the complete infrastructure to build the APIs, and they also integrated the OAI into the system. And coming back to this same architecture, if you want to put back to the old, it is just an add-on to this IMX system. So everything what is there 4 years back, which we defined, same thing exists. The only thing is the new NPU is coming to picture. So this is where the OpenAir infrastructure can come in, and we are working with multiple partners here, DFKI, RPTU, Lime Micro, and also universities from Bremen, Berlin, Dresden. I think we are working with all of these universities to enable the OpenAir interface to get into this one. They are using this in multiple 6,500 projects. And one or two examples of what I would like to give you is, it is okay to have AI to run. Where? If I am running my system in a simulated, it is okay for the research. What if you really want to test your own waveform? If you want to try your own application, can existing platforms give ability to change the code to the lowest level? For example, I'll go back to the slide. I said here the DSP. The whole DSP program is open source from NXP. You can also modify. The DFKI is already taken, and they are modifying the DSP program. Means the infrastructure to write your L1 layers is available in the open source, and it is BSD3, means it is permissive. You can change it. You can also commercialize the way you want. And with this kind of thing, adding in AI devices like ARA2, we can already build the AI learnings into the system. You can create your own waveforms, test your own waveforms, or even do a real-time system evaluation. For example, here, a running system, your RA detects, the AI detects that something which can be improved. This code can be updated in time, in real time, into the. It will also build. The code is built, checked again, inside the device, also be uploaded into the device. It's not going outside the device. That's important. You can also build simulation environments. For example, if you want to do an inferencing, if you want to do a training or anything else. I'm not an AI expert, so I'm just using the big keywords of AI. I'm still a novice in AI. So such models, we can define, you create the data sets, you can create the workflow into the system, you can build a system around it, integrating the thing, and think about how an open-air interface can also play a role here. For example, everything is open source. You guys can modify the code even to the lowest layer L1. I just want to end with a few notes. I'm done to the last device here. What we believe here in the smart device, I'm not talking about the infrastructure side. Please don't kill me for that statement that more TOPS is not needed. In the smart devices, in the embedded devices, in a very, for example, you have a smart device for your glucose control. You don't need too many TOPS. But AI at that edge needs, a very particular power, the compute power, just as it needed. You don't need too much. So that kind of thinking is needed. As an open source developers like you guys, the OpenAir interface can also think, not just thinking the OpenAir interface in the G Node B side on the network side, think also about the device side. The opportunity to create the end device specific to the smart device and specific to the need of the hour. You have hundreds and thousands of applications you can build, and you can have your own applications. Like for example, I don't know whether it's right to say it like this. In Apple Store, in Google Play, how many applications are there? If the Apple can write their own, drawing applications or writing application IDE, nobody else of the developers probably needed it. But every other application you see in the Apple Store or in Google Store, you have very creative applications. So think about it. You can write your own devices up to the lowest layer. You don't need a full stack. You can optimize the layers. And again, because we are talking about the end device, I just want this at the end. The power is very important. Now, I'm also not talking about the environmental issues. Of course, it is contributing it. The low power is a superpower. Means as you write a code, as low your power usage is, your productivity of the device will be improved. Means you need to put a lot of effort to make your product to consume low power, right? And again, as I said, we have to be in the options we've been thrown at. Don't just choose which is available. Just make a right decision, which device you want to use, how do you want to do, what is your target applications are. That's make it right. So, and here I have I would like to give a stand-up ovation to the OpenAir folks, because the first time I attended OpenAir interface workshop in like 21, 22, and that time, Florian took me to the lab in Eureka, and we were excited to see all the new things coming up from the 4G to 5G at that time. Now today, I see a lot of real demos. And the real demos are getting here. I'm very happy. And this is exactly what we also would like to support. We would like to open the sources, for example, NXP's DSP code or the layer 1 code, what I'm talking about. It is well tested. It's been, for decades, it has been reviewed. And now you can use this to create your own AI-based. You can feed it to generate your own modules. But at the same time here, I would say that OpenAirInterface, you guys can pick up this kind of low-level code from us, generate, build it, try it how you can also get integrated into your system. And the last thing I would like to say is, from my point of view, in my organization, we are now more focusing on the robotics side. And robotics is having multiple form. It may be robotic arm, humanoid, your AGV, EMA, all that. All this requires multiple domains. It's not just we have an arm which is doing pick and choose, but itself coming into communication. It needs smartness, it needs communication, it needs real time. All things that we require in the communications are also coming into here, to the robotics, all the things we are talking about, the end devices, smart devices are taking a form. It may be a drone also, right? So follow us on robotics. We have a lot of openings in the NXP. So anyway, I would like to thank you. And I hope I just gave at least a device side perspective from my system innovation point. And hope to see you in the next workshop and see more progress soon. Thank you.
Are there questions? One question.
Cool. Thank you for the talk. So I think somewhere you mentioned about the EUICC chips, which has a SIM profiles, right? So I just wanted to ask, is it a single MZ profile or it's a multi-MZ profiles?
It's a UICC as our architecture is multi-core and multi-targeted thing. For example, you can have multi-profile included. And I think the question is more about, can I provision it?
Correct.
I think
that's
where you are coming up. Yes and no. Yes, as in test profile, you can place it, but this will not solve the GSM standard. Mm-hmm. So if you need to have a GSM standard SIM, it has to be certified, certificates from them. Then you have to use the right path. But if you want to do your own testing, yes, we have some capabilities to tell you how to install your test profiles, configure your keys, which is good to go.
Okay. And just one more question I have. As like the industry is moving towards integrated SIMs, iSIMs, to save space and power, so is something NXP is working on, or you have something like this in the future, or you have a current device which supports integrated SIMs as well?
I am not the right person to answer that because SIM itself is a very big department in NXP. What I can tell you from the very top level is all these things are welcome. For example, we cannot stop the things which people really want. If the mass wants, it's going to get it. So I'm not, anyway, my answer is my personal, but there is a big department in this thing. Even though I worked for 10 years in the secure elements previously, I cannot answer that. Yeah, sorry.